just going to hail. I bought a new truck. Yes. What's that? I got a Sierra. It is. Yeah. We got rid of our Silverado and went to the Sierra, so I'm happy with it. Suffice to say. So, there's three possible things that can happen when you have solved systems of equations, and we're talking about two variables. When you solve system of equations, you could get, obviously you're graphing lines because you're on linear. They could intersect at one point. The point at which they intersect is when they solution. So it could happen with one answer. You could get what does that mean? Parallel, which means there's no solution. Now, the reason why they want to become parallel, why are lines parallel? What do they have in common? Slopes. Now, when you're going back to slopes, one of the things that we've done is we've got two different types of equations. We have the mx plus b, and then we have the ax plus by equals c. Now, obviously, when we're talking about slope-intercept form, the m, that's an easy slope. Okay? The standard form stuff, excuse me, the standard form, remember how we did this again? Very good. Your slope here is always the opposite of a over b, right? That will always work for those. So, and then the last one you could get is when they become the same line, which means how many solutions do they get?
Yeah.
Yeah, the answer is yes. They're infinite solutions. So we can have one solution for when they intersect, no solution. That's because they're parallel. And then this would be infinite solutions. Okay. And again, something that you guys have all seen. A lot of times with the infinite solution stuff, what they'll do is they'll have two equations that look very similar, where they might have a common factor, something's just been scaled differently. So you probably, a lot of times you can kind of figure out that they have to become the same line without too much work. Or if you get like 7 equals 7 or x equals x, things like that. Now, graphing. What's that? I sense the sarcasm. So let's take these two equations. 2x minus 2y is negative 8, 2x plus 2y is 4. And let's see what happens. Now, when you have those types of equations, you can graph them how they sit. You can simplify them if you'd like, if you can. Is there any reason to put those into slope-intercept form at all? Because we all know how to do what? The cover and solve stuff. You can do your intercepts. Okay? Now, excuse me. I like how you said with the slope, because we can get our intercepts, and once we get our intercepts, we can then walk the slopes between everything to create all the rest of the dots. So it doesn't work out to be relatively simple. So if you do your cover and solves with the first one, I have a y-intercept at 4. I have an x-intercept at negative 4. Are we okay with that?
Yes.
So y-intercept at 4, x-intercept at negative 4. Now, between those 2 points is the slope, isn't it? Couldn't you just count that? You had to go up and over. You went up 4, over 4. So what's your slope? 1. So we know that our slope here is 1. So as we go through, when you're solving systems via graphing, a lot of times it's easier to just put the dots on the graph paper like that, fill it up, and not draw the lines. Okay? The reason why I don't like, what? It's okay, no. The reason why I don't usually draw the lines when I'm solving systems like this, when they're linear, is because I'm looking for where they run into each other. And sometimes it's cleaner to see it if they land on an actual dot, because when you graph them and your lines, sometimes your lines don't match up all that cleanly. It's not the most efficient way to solve things, but I try to just use dots. But there's nothing wrong with it. And then same thing here. Y-intercept at 2, X-intercept at 2. And then this one shows us that we're going to have what kind of a slope? -1, so the slope here. And looky, we found out where they ran into each other right away. Don't roll your eyes at me, Coleman. I try to have some calm here. So your solution here would have been at, what is that? -1 and 3. Oh, ladies and gentlemen, when you graph stuff or you're using ordered pairs, what comes first, X or Y? X. So X goes which direction on the graphs? Horizontally, left and right. And then Y's go vertically. So sometimes when you're writing ordered pairs, you have to make sure that you know that difference because some of you guys forgot that difference when you're doing that quiz on Friday. So I've got a couple people that are left to get those in. Hopefully I'll get those to you guys tomorrow. I should be able to do a talk about that. So. Does vaguely ring a bell about having to do this stuff? Yeah. All right. Well, let's do. Here, try this one. 2x, 4y, and a 12 equals 12. And x plus 2y is 6. Oh my god. Oh. I really do. It's really not safe here. Yes, it's super unsafe here. Gee, what happened right away here, guys? I'm the problem. Do you need to do any work here, guys? No. Did you guys recognize? For some reason, I don't think you recognize it. Infinite solutions. Okay. Again, it's something if you recognize, it's great. If not, as you go to graph it, you would have recognized it right away. So, darn it, I just wasted my time. But hey, that's okay. What happens when we get stuff with halvesies? This is where I wanted to kind of, when you start to see now, when you get into one like this, when we've been accustomed now to kind of doing the covers and solves for finding intercepts, that first graph is going to be kind of weird though, isn't it? Because you're going to have a halvesy for an intercept. But if you manipulate that equation, can't you get it into slope-intercept form relatively easily? And that's kind of what happens sometimes. It's totally up to you, but if I know that I'm going to have a halvesy for intercepts and stuff, I might just move some stuff around real quick and know that this is going to be the same thing as y equals 2x plus 5. You know what I mean? If I do something like that, then I know, I'm still going to go through the intercept, but I'm going to be able to plot the points maybe a little bit cleaner. Again, it's totally up to you, but when I see stuff like that, I do it that way. What's that? Well, we're doing algebra. We're doing graphs, right? Yeah. Hello again. Sir, you're shaking your shoulder. And then the other one would be relatively simple. You're at 2 and 2. And this one has that slope of the -1, and you'll see right where you run into it again. Oh, that's the second one. We had the same spot. Maybe I'll put a star in it. There. Oh, just star. Beautiful. Thank you. All of our answers won't be always at -1 and 3. Let's make us look like it. Children are at a bus stop. Yeah. The neighbors take them down there, so they're probably in a car. So now the other thing, as we get into a lot of this stuff, we know that as you're doing the graphing of these things, it's not always the most efficient way to solve. When you get going, though, you're probably going to wind up doing a little bit more of the solving algebraically than you will graphing, because then you can deal with the numbers a little bit cleaner. I still want you guys to be able to graph stuff if need be, but I think that when we spend more time actually solving algebraically, it becomes a little bit easier. Because like we were just saying, you can use elimination or something along those lines. Now, when we deal with the algebra stuff, remember there are 3 different ways of that as well. You guys remember those? You can add them, subtract them, or do some sort of combination. And that's kind of where you're getting with that. So the way that I always look at it is, or I'm sorry, there's also substitution. You can put something, bless you, you can put something in for something else. Now, the ways that you're looking at solving systems, though, you've got, if you have the same sign, same coefficient. What do I mean by coefficient again? Yeah. Then I would subtract. If I have the same sign, same coefficient, I would subtract it. If I have opposite signs, same coefficient, I add. Okay. And then obviously there's other ways of going about it by doing some linear combination stuff. What it means by linear combination is that you're going to create the same sign, same coefficients, or you're going to create opposite signs with the same coefficient. It's totally up to you when you start seeing these things what method to use. One method doesn't always mean it's the easiest. One method might be faster than another. It's just the worst case scenario with these types of problems, to be honest with you, is when you're reading the problem out of the textbook. You'll look at the problem, you'll write down the numbers, then you'll look up and you'll look at the wrong number. This happens all the time. Okay? So if you wind up getting really bad values, you probably wrote the problem down. It happens more often than you would ever think. So if I'm looking at just this one, we'll start with this guy. This one automatically. Smartboard. There you go. You guys will be okay. I don't think Lincoln will go there.
I don't know. We're going over here. Yeah. It's perfect right there.
I'm sorry. Hey, why don't you guys just lick the metal around the window? Kind of then. No. You ready? So, in this case. Are there same coefficients anywhere here? No. But there are same signs. So in this case, what would you do? How? subtract, but what would you do first before you subtract? You're right, but I can't subtract it because I don't have the same coefficients. I got to make the coefficients.
To the second one.
Oh, okay, all right. Okay. What she's saying, guys, is take this one and just multiply it by -3. Does that make sense? If you do that, you got to make sure you send it to all parts. Most people will get the first, you'll never forget the other side. So you wind up with, I'll rewrite the first. -3x. All right. And then I like to split it, so I have 3 separate problems to do. It helps keep your signs straight. -3 and 3 is gone. Here we get -2 equals, what is that, -10. So y is 5. What do we do with that 5 then? Put it back here. You doing electrical work?
Yeah.
How about substitute? Substitute back in. Doesn't matter which equation you choose. No. As long as you do it right. And then, do you remember the rule for writing your solutions out for these things? Great. Ordered pair. Okay. Yeah, an ordered pair. All right, that's what it looks like. So yeah, plus or minus, it's close. All right. So far, so good?
Yeah.
Okay. Do this one. Do that one, please, and thank you. Yeah. I have a feeling your conditioner just went out.
Oh, man. Let's go.
I can just already tell that it's getting stuffy. It's gross. It's just gonna be a gross, sticky, sweaty day. It's gonna be probably today. Oh, hey, sophomores, you guys have class games today during flex. You can't flex out it. You guys are meeting with the deans. I know they're the worst.
I don't want to.
Where are we going? I don't know. It's not my job. I just told you can't flex out. I didn't read that part of the email. All right, so what you do here? Bless you. What I would have done, I would have multiplied the bottom one by 2.
By 2 or negative?
Oh, I'm just going to go by 2. I'm going to show you how I do subtractions. It might be a little bit different. If you did -2, that's fine. No big deal. Because then I'll rewrite the top. And then I have 6x. The way I do subtraction is I split it up into the 3 problems, and then I put the minus sign in between each one. So then I get 4 minus the 6x. So I get -2x. -2 minus a -2 becomes plus a positive, so you get those crossed out. And then -1 minus 16 would be what? negative 17. Okay. And then you get 17 over 2. And from there, I would substitute that back into the first equation. Reason being, when I'm sorry, that way, when I take 4 times that, the denominator's clean up. So it should work out. Let's get 4. So let's see, that becomes 34 minus 2y. So negative 2y is negative 35. Was it 35 over 2 then? Yes. It just kind of crummy looking values. That makes sense because if you throw this back in, we knew that was 34 over 2. I'm sorry, that was 17 over 2, so that would be 34 minus 35 is negative 1. So as crummy as those values look, it's still pseudo clean as we go through it. It's still not too terrible.
Forgot to write it as a.
Oh, yeah, I'm sorry. Thank you for reminding me. Ordered pairs, 17 over 2. Good morning.
Good morning. Hey, Sierra.
Oh. Would you please hurry up so we can talk badly about you? Oh, very good. Okay. Whatever numbers I have close, I'll have close up here. I wasn't sure how fast I go through, so I express. All right.
I don't know.
Now, here's a top tip. Notice you have a plus and a minus for the y value. What could you do right away as you're writing down the second equation? How? Correct. As I write down this problem, what I would do is I recognize right away that I've got the opposite signs of the y values, and then as I'm looking at that secondary equation, everything's even, which means I can take out a 2 across the board and it'll be fine. Okay, it's just a scalar, is what we would call that. So as I'm writing this problem down, what I would do is 3x minus y is 13, and then I write down x plus y is negative 5. Okay. Again, the reason that I do that is because it's just a scalar that I'm simplifying out. And then here, split it into the 3 parts, and I'm going to add them together. Okay. When you do systems of equations, a lot of times it's a little bit nicer if you space it out a little bit more between the problems, so you get a little bit more room. And then let's see, 3 and 1 is 4. And what is that, 8? So if x is 2, and then what do you do to figure out y? Substitute back in. So y would be what, negative 7, right? So ordered pair. Yay! Mighty roar comes up and out. I think we're okay with this then. I won't have to do more of the alpha. Oh, I know. Give those a shot. I didn't put any of the graphic ones on there because, in all honesty, it is more efficient to do it algebraically as we go through. I got the textbook up here if you want to take a picture of it. I'll post it up here real quick also, so you guys can take a picture of it there. But I do have the what is it? PDF files are on the calendar for today. I'll pull it up here. I think it was 44 it started at.
It's not even starting.
Here you go. Really fun. Really fun. There you are, ladies and gentlemen. Woohoo. Woohoo. Or if you just take a picture of this right now, you have everything right.
What you want to see what my camera looks like?
No?
No? Show it. It shakes and it makes a noise.
Nice. Sounds like fun. I watched part of it. I didn't watch all of it yesterday. We were outside just doing so much stuff around the house.
I was pointing down.
You went to the game yesterday? It was beautiful, Dave. It was gorgeous out yesterday.
Yeah, we went to the soccer game.
What did you do?
You guys hardly get a job.